a lot of breakthroughs and a lot of discoveries had to be made. Every day, AI and AI-based models are getting better and better at problem solving, and in parallel, there are more problems emerging. And now we'll hear from the General Director of AIRI, Skoltech Professor Ivan Oseledets. Please give it up for Ivan. He will talk about improving the efficiency and quality of training large neural network models. Hello, everyone. When I was preparing for this lecture, for this presentation, I was thinking about what ideas I wanted to discuss here on stage. I could talk about the big breakthroughs in AI. You've all heard about it, ChatGPT and large language models. Contrary to that, I would like to focus not just on the achievements, although I will mention achievements, but the interim stages towards the big goal of creating AGI. I'm going to have several sections in my presentation, and if you get lost at some point, you'll be able to catch up with me during the following section. And as a matter of fact, I would like to begin by saying a few words about the status quo of neural network models. We all know that they are phenomenal at problem solving in classification, prediction, and segmentation. Same goes for text. For working with text, the two modalities, text and image, basically this is the problem that we have already solved because we can do anything with it. The next step, which has already been made by many, but not yet fully implemented, is creating multimodal models. I would like to present the first of this kind in Russia, developed at AIRI, at our research institute, called OmniFusion. The idea behind OmniFusion is as follows. We combine two modalities. We combine text and image. We combine it as follows. We upload images, and then we start asking questions. What do you see in this picture? What is the temperature reading? What do you see on the thermometer at all? And it can support that dialogue. There are equivalent systems in the world. Most of them, such as GPT-4v, they are closed. There are some open systems. For example, there is a system called Lava. We took that model and we compared it with ours, and what we got was a very decent result, but I'll talk about it a bit later. First, about how do you build a multimodal architecture? Three approaches. The first approach is the simplest. We have a language model, our LLM, and then we also have systems that can process images. For example, Kandinsky, which can generate images. So there is a set of models, each trained in its own modality. There are no multimodality in it. LLM works as an orchestra conductor, as an orchestrator. So at some point, when it was prompted to draw something, it thinks, okay, I need to draw something, I need to call an external model. If it needs to look up something, it needs to connect to the search engine and get the data from there. We know how to organize it technically, but the problem is that there is no connection among the modalities, which is key because there is separately there's text, separate images, but there are cases where images and text are located in the same data array. The second approach, called end-to-end, involves taking large multimodality data sets and then, through tokenization, we produce long sequences. For example, there's an image. As Vision Transformer does it, it is broken down into patches. Each patch is transformed into a vector, and then the vector is combined into this long text, quote-unquote, in order to train the large language model. The modalities are very much interconnected, and this way you can get a lot of results. There are a lot of articles published about it. You can combine not just text and image, you can also combine text and graph, text and video, text and planning robot motion. But In this case, training takes a lot of time. So basically, we need to train a new large language model from scratch. Even though we have a lot of such models, dozens of them, still, training, I will return to it in a minute, training them may take dozens of millions of dollars. This is only affordable to a small, to a handful of companies in the world. And the third approach, which is the most efficient, as we believe, this is when we use encoders, which help you convert an image into a vector. You can use the well-known clip model as an encoder, and then you build small adapters, which are essentially a small neural network and which translate this vector from the image language into the text language. So we start with a well-trained, pre-trained language model, and we train only the adapter. The training cost in this case is thousands of times less than with the end-to-end approach. The quality of the modalities is a bit less. I will not go into the technical details. Andrei Kuznetsov is going to have a big report. Andrei from Fusion Brain will have a big report about the internal architecture of OmniFusion, and he will take your questions. But in just a few words, the table you're looking at shows that there are closed models. They work very well. Yeah, so roughly speaking, they can answer the question, what do you see in the picture, very well. But we want to compare our model with the well-known openly available models that use GigaChat 7b, which by certain benchmarks are better than Lava 13b. It's not there on the slides, but I'll just say it, that we used 2 GPUs A100. It's a bit laughable today, but still the quality of the adapters is pretty high. The model continues training, and the quality gets better and better with time. And once again, I will let Andrei Kuznetsov to talk about it in more detail. This shows that OmniFusion, with a number of metrics, is ahead of the main openly available multimodality model, Lava 13b. If you look at the computing power and the data size, the numbers are hardly comparable. This is pretty awesome. I promised to tell you about what we do and what are our goals, but first, a couple of words about our achievements. And now the goals, essentially. What do we aspire to do? A true multimodality model. Multimodality has to be an integral part of AI. A true multimodality model should not operate just 2 or 3 modalities, but if we dream big, it should be able to handle an arbitrary number of modalities. So we have a pre-trained large language model. We give it a new data set with a certain modality. For example, we want to add video or sound to OmniFusion, or we want to add graphs, or we want to add anything, I don't know, protein related. So we take the small data set and we want to train the model additionally using this new data set. And the model understands very quickly how to work with new modalities without having a fixed number of them. So they can work with just a byte flow. There have been attempts to achieve this, unsuccessful so far, but I think that very, very soon we will see some great progress in that area. I hope the progress will be made by us. So multimodality, just to reiterate, is essential. It has to be there, but it has to be true multimodality, not just 2 or 3 modalities, but an infinite number of them, and the model should be able to handle them. I don't think it sounds like sci-fi. It's not fantastical. And working with adapters, the adapter-based approach, I think, is the right way. What else are we planning? What are some other ambitions that we harbor? This exciting area, still lots of questions without answers in it, but a lot of promising things to do. Multi-agent systems. Why multi-agent? What we have now is this huge model. It's getting more and more huge. 10 billion parameters, 40 billion, 180 billion, trillion parameters. It's getting bigger and bigger. We want to create an AI that knows and understands anything. Anything and everything. Speaking of humanity, humanity is not just a single super brain. Humanity consists of many, many people who interact with each other. The success of humanity is not just driven by one person. It's many people who can cooperate and communicate. So do we need an architecture, a similar architecture of many models? Or can we just train this supreme, huge, unified model? Still a question. But we know that as the number of, as the data size increases, as the model gets bigger and bigger, the quality of its output also increases. But we cannot increase the size of the model indefinitely. Our computing power is limited after all. And if we speak about it not in academic terms, but in practical terms, training a model with 7 billion parameters or 180 billion parameters, the difference in cost is hundreds of millions, not just dozens of millions. So if we compare the quality of models, pre-trained models, and if we try to combine them in a common environment, that I think sounds more realistic. So far, it looks a bit like assigning roles. This model is good at this, that model is good at that. Let's create prompts. I'm sure many of you know about it. How do we ensure exchange of information among them so that with certain benchmarks we get more accurate answers?
Well, actually, we had this idea in summer, quite a while ago. There was a famous post in the social network that used to be Twitter, by the way, the post that in GPT-4 mixture experts are used. So there is a number of models that I use in different parts of data sets, and there is some exchange scheme between them. Now, this exchange scheme does not have any complex interactions like human-to-human interaction. Now, do we need to copy people? Well, we are limited in terms of compute. We can train 3, 4, 5, 10 models, and, well, this is a very promising approach. There are many approaches, many options like LangChain, role-playing, and role assignment, where manager, tester, developers' roles were defined, and these roles were given to a language model. And now they have the system that writes code, efficient code, but it will be great to have a less engineering thing, because the AI development is kind of moving along the following trend. We want to remove the manual prompts. We want to automate things to have less, to have fewer customizable buttons. Now, there are some interesting mathematical problems here. Now, one language model, what does it do? It models the distribution, expectational distribution, for the sequence of words, and it knows whether our answer is true or not. So it kind of models the distribution. Prompts technique, like I'm a physician, or give me the right answer. So we put it up front, and after that, the model starts to generate. But if we put a prompt, we found a model within another model. And that's also a distribution, a conditional distribution. So we have a model that has been trained by someone. We do not know who trained it and what data was used, were used, but we have different personalities, so to speak. It's like a schizophrenia in a way. So many small models in this one big model. How can we find all these personalities within one model and then classify them? And after that, we can be used as agents. So kind of have this sum of different personality within one model. Amon Shasho looked at this from a mathematical point of view. And that's a very interesting point, because this is one of the few research papers where they try to theoretically assess and evaluate the properties of a mathematical model. So in a nutshell, the result was as follows. Like, you have bad behavior, something that does not comply with the Russian law. And this model might do something like that, but we obviously don't want to prevent that. So if it's not a zero, that it will have this result. And this alignment procedure is not possible here, because you can put the prompt that would put it to 1. And if there are no external filters, it's not possible to do it as part of one language model. And there was an assessment of the prompts, and the foundation of this theoretical structure is the deconstruction of this behavior in several parts, racists and not racists. Our task right now is to make sure that you find this internal structure, like a clusterization problem. How do you do it mathematically? I have not yet come to a decision on how to go about it, but I think that this is one of the most promising fields, really, and we can expect some breakthroughs here. There were, some engineering solutions or data where processing solutions should be used. They might be different, but this is a very important area for development of AI, and the results here will be a breakthrough. They will be disruptive. Now, what actually happens? We need to develop multimodality, multi-agent nature, and another thing we need to do is to decrease the training costs. And the second part of my presentation, I'm going to go back to the to my scientific roots. I have been doing linear algebra for my whole life, and how do you train this large neural network quicker while minimizing the compute? Now, why is this an important issue? It is important because the efficiency of the training, even with the use of the best and state-of-the-art frameworks, the efficiency is 50% max for the large models. So you have a graph card, like a graphic card's GPU, and then it uses 50% of its capacity. If we like 50%, it's actually very optimistic. It can be 30%. So we might increase it by a minimum twofold. That means that the compute capacities are just staying idle. Now you can say that the complexity and the size is growing exponentially. This trend continues, but training several models with the same solutions, the same, so to speak. Maybe we're not going to have this several trillion-bit models. 7 billion, 13 billion, 40 billion. These are the parameters, numbers that we need. 40 billion model will be 384 S2, and you need 2-3 months. Falcon 40B, that's the time. Not all people have 384 S2 that you can use, because you want to have some results quick, and we have made some tweaks. And on ICML 2023 conference, we didn't participate. Our Chinese PhD student went there because no one else could get the visa, and he was working all the time for us there. Not that he suffered much, but anyway. Anyway, what is the idea here? You can modify the calculation algorithm for gradients for a flow non-linearity, and instead of 8 bits, instead of 16 bits, you can use 3 bits. At the same time, the accuracy will remain the same. So this is the thing that is integrated in any code, and it drives down the memory load by 5–10%. And memory is the main limitation here. Another research paper that we have not yet published is using randomized nonlinear algebra to accelerate the computation of gradients of the large linear layer. So you understand that this is a multiplication of the matrices, so you can calculate that approximately if you make this multiplication. And for the stochastical gradient descent, it's not that much of a problem, because if you train large language models, the large matrices are being multiplied, and in this algebra there are methods of its multiplication. But it's not accurate. But we don't need accuracy all the time. If you can unload some of the memory, because memory is the main limitation. 1 gigabyte for the, so not enough for the GPU. And at the same time, you make sure that the model is still accurate. Now, these are some of the quick tweaks. Another result, absolutely fresh result for using fast lower adapter. If you use the adapters, that's a very simple code with 3 lines. If you put this matrix multiplications in the right way, you can decrease the time for the training by 3–5% without changing the accuracy of results. So without changing the algorithm, you change the order of the transactions, of the operations, and that means quicker algorithms without losing the accuracy. Sometimes we can make the algorithm quicker by losing the accuracy, but this is not the case here. So it's not like one big, huge idea that drives down dramatically the costs that is used by the ML. So this is a kind of a ML package, so to speak. A bunch of solutions that decrease, improve the efficiency by like 2, 5%, 3%, and so on. Is there a big idea, some big idea that might increase and accelerate the speed of the training of the big models? And we think it is possible. Alexander Mikhalev, assistant professor of Skoltech, is working on that. It's called N-Tile. What do we want? We want to re-implement the basic operations, all layers, using Python or C++, maybe Cicuda, and starting from the scratch without using Python, PyTorch or big packages to maximize the efficiency and the performance, and use multi-processor systems, maybe the systems that would not use A100 cards, like 3 A100 cards, 4 cards that are not as modern, like heterogeneous environment, by using all the resources that we have. So this is what we do. This is the idea. the task-based parallelism is to make sure that we have subsets of the problem. How do you dynamically distribute these parts of the problem for the calculation? It is done by the planner, and no one has ever done that before. We try to do that. Now, that's a basic idea that we have for the task-based parallelism. The Kolesky factorization, that's a simple task. You have the tiles. We divide the tasks by tiles, and then there are rows. And what can happen, really? We have one task, and that means that quite a large matrix will be multiplied by another large matrix. When you have the result, you can take a different task. But if you divide them, you might ensure that the scalability is quite big. I don't have a lot of time, but I'm going to say that if we're doing that for NNs, we have a graph that is much more complicated. That looks here and plan it, and the basic block in NN training is multiplication of matrices. It's not like that here. Every matrix is divided by small parts and then multiplied by each other. So the graph becomes a much more difficult thing, and you have to implement that, to plan that, to draw the basic blocks in a proper way. And we have done the majority of these tasks. Now, under the hood, we use star PU framework. Instead of PU, you can put GPUs, TPU, NPU, whatever PU you have. If you have the access to Huawei processors, then you can do that. So whatever, star is like the asterisk means the asterisk here. So you can fill in the blank, so to speak. Anyway, that will mean that you will use statistical graph, and based on the communication between the nodes, the planner will be able to resolve this planning task. And in 0.1 version has been implemented. All the transformers, all the optimization methods, it's all integrated in Python, so you can copy the checkpoints models.
So far, it has been working with just one node. The computing equipment that we have is 8 800. We can use these 8 800s to train a sort of a small GPU too, with some modifications, but not radically different from the standard model. And it gives you 80 to 90% effectiveness in just singular accuracy. It's interesting that one of the main advantages is that we do not have to concern ourselves with memory. While the interim layers fit in the CPU, the GPU memory stays the same. So the overall memory needed for training is roughly 500 gigabytes, sorry, for all the training steps. Our model can do with much less than that, and it's all under the hood. The developer, after implementing the basic blocks, simply has to move these basic blocks and change their places. The loss is going down. Overall, we are satisfied. We will, of course, be moving from 80 to a bigger number. It will require a lot of work. If anyone is interested, I can provide the technical details. But it is still working, and it can already be used for fine-tuning, for example, of large models with a small number of GPU. Do not worry about memory. It can be redistributed. It can be used for inference. You take a large model, you break it down to 4A100, and it can already be used. Future steps, we want to add the support of half accuracy, 300 teraflops, to 1 GPU. We move from 8 to a bigger number of nodes. And the key goal after that will be developing our own planner, our scheduler. We want to make our version publicly available for people to use it. Thank you very much for your attention. I'll be happy to answer your questions now. Thank you for this impressive session, Ivan. So as a user, what I understood is that we are looking forward to the development of multimodality. Of course, we received a lot of questions. I'll have the time to read out just a few of them. What are the mistakes in model training that you've experienced? The mistakes that are the most dangerous? Insufficient number or incorrect data processing or lack of balance? Well, in training a model, of course, data is key. Well, there are two things: problems with the data, with the architecture, and there are also problems with training that result from this. Problems can arise anywhere. It could even be the change in PyTorch version. That may result in overfitting. So lots and lots of sources of errors. But most often, we as people who work with algorithms, who primarily focus on algorithms, the most common mistake is incorrect calculations of operations with a floating point. Okay, question number 2. What are the methods that are the most efficient in solving the problem of overfitting? Well, this is a question, it is still a question without an answer. There are a lot of small models which show good results with benchmarks, but they are simply trained with a training set. Still unclear, is it good for a model to be overfitted or not? Okay, the model has remembered all the training data sets and gives you the correct answer. Yes, and there is also the emergence factor. Of course, it would be good to describe the formality of it, because basically what it is probabilistic distribution based on sequences, and it is still very much unclear. How does acceleration impact the accuracy of approximation? Ideally, we would like it to have no impact at all. In practice, it goes down a bit. Thank you very much. We have a lot of more questions for you, but no time left, unfortunately. Lots of interesting topics to hear about. Ivan Oseledets, thank you very much.